Hello there. In this video we're going to do a bit of a blast from the past, Unit 7 cash flow problems, but the technique that we're going to use at the end to solve for it is going to be logarithms. So in the context here, Nisha is moving to the States and she really wants to start a Roth IRA, and she puts aside $5,000 a year, 5% annual growth rate. How long before it's $1 million? So let's start by modeling, trying to figure out what the equation is, that there is this every year that we're putting in $5,000, and that's growing at 5% each year. So right in the beginning, we have $5,000. No time has passed. In 1 year's time, that $5,000 will have actually grown by 5%. So you can think about, this is sort of building onto the right, but you think about this as the original year. That first input of $5,000 has grown by 5%, and then at the end of that first year, we put in another $5,000. Then another year passes, and we put in another $5,000. Think of it this way: that first $5,000 has grown over 2 years' time now. And then 1 year later, we put in another $5,000. That's grown a year. And then we put in that next $5,000. This keeps going. Now, I find it a little bit confusing because this is not the original $5,000, the way that this problem reads. That this is the last $5,000 we put in. This one here is actually the original $5,000, which has now grown for 3 years. And then that first year we put in $5,000. That's grown for 2 years. Last year we put in $5,000, that grew 1 year, and right now we put in another $5,000. And then this just continues. And we're not sure how long we're going to do this, so it's going to go on here to the nth year. And that will count the number of years, because remember when we were 3 years in, that exponent there was a 3, and then we had the 2 year mark, the 1 year mark, and then what we put in right then and there. So, long cash flow problem. But if we remember our Unit 7 techniques, we know how to solve this kind of thing. If we don't remember the Unit 7 formulas, we can always derive them. So remember, I take that big sum of money. My growth factor in all of this, what I'm multiplying by, is 1.05. That's that 5% growth. So whatever that sum is, when I scale it by 1.05, this 5,000 gets scaled by 1.05. This number is scaled by 1.05. That becomes 1.05 squared. This one goes up to cubed, so on and so forth. And at the very end, where we had n, that's now going to become n plus 1. Okay, and the technique here was to do a to do a combination. We'll get stuff to cancel out. So in subtracting them, this first 5,000, that has no pair, so that's just going to be 5,000. But then everything else actually pairs up. Like that's going to cancel with that, that's going to cancel with that cancels with that, so on and so forth. This is going to cancel with something right before it, but this one doesn't have anything to pair with. Alright, so there we go. And then remember, we can do a little bit of factoring and divide, and we'll solve for our sum. Now if you happen to remember the formula, that's awesome. Because I guess you could do that saying, okay, there's n years, so we're going to raise that to n plus 1 there. N years? That is n years, because 1 year we have 2 increments. That's right, that's how that works. Because we are sticking that $5,000 at the end there. And that's 1 minus r to the n plus 1 over 1 minus r with that 5,000 out in front. Okay, so how long before we grow to $1 million? We're going to stick in that 1 million over on S. Okay, different ways to go about it from here. I could evaluate what this side becomes. 1 minus 1.05, that's going to be negative 0.05. Actually, let's just do it where we divide by 5,000. In the beginning, and then also clean that part up. Okay, so we're doing baby steps here. That's good. Okay, multiply through by that negative 0.05 on both sides. Oop. Okay, I'm getting lots of negative numbers, and I absolutely hate negative numbers, so I'm going to add them to each side. Get one positive 1.05 to the n plus 1 is equal to 11. So I'm just adding 10 to both sides and adding 1.05 to the n plus 1. Make it all positive, hate negatives. And now we have an exponential equation, and we can start bringing in our logarithms. It's not log base 10, so let's make it log base 10. 10 to log 1.05 will just be 1.05, and then we got that n plus 1 over there. There's our 11. And now we can take the logarithm of both sides. So the log of this 10 to something, that's just going to be our exponent. And then we can divide. And at the end, we're going to have to subtract that 1. And this is about, when all is said and done, typing in 48.15 years. So a little over 48 years. 49 years will be good. Okay, I just double-checked that by writing a next now rule for this thing. That next now rule was next equals 5,000 plus 1.05 times now, starting at 5,000. And I mashed the enter key a whole bunch of times, and right at like the 48th entry, it was 990-some thousand, and the 49th one, it was over 1 million. So, pretty confident in that. Thanks for watching. Character and Scholarship for Life.